Hey everyone! Today we'll be solving the slide puzzle problem with the A star algorithm. A star is a pathfinding and graph traversal computer algorithm that plots an efficiently traversable path between many nodes. It's well known for its performance and accuracy and is widely used. It's commonly used for a variety of issues that can be translated into graph form and have accepted algorithms. I'll start with a general discussion of A star and its basic algorithm. Then we'll go over how we have used the A star algorithm in our Dart code. We'll also take a look at visual examples. Let's go through the advantages of A star algorithm. It will always find the best answer if one exists, and if a heuristic is specified, it must be acceptable. Heuristics aren't required, they're just employed to speed up the procedure. Without modifying the fundamental code, several heuristics can be incorporated into the algorithm. The cost of each step can be changed as easy as the heuristic in the algorithms. It isn't limited to a single direction search. Let's look at the disadvantages. In terms of memory and processing, it's not the optimum approach for each task. Because each node produced must be accounted for, it consumes a lot of memory. The slide puzzle is represented as a matrix. For each configuration, there may be multiple valid moves. In this case, there are two options to move the empty tile, either right or down. For this configuration, there are four options to move the empty tile: up, down, left, or right. There are a few important terms that you'll need to know to understand the A star algorithm. First, the G score. The G score is the cost of each move. It will increase by 1 if the cost of each move is 1 at each step, since each tile is sliding onto the blank space represents one move. And in the end, we need to get the optimal moves for the puzzle instance. This basically means we'll have to add 1 to the G score of the parent before storing it in the child nodes. Manhattan distance of a tile is the distance or the number of tiles away it is from its goal state. Thus, for a certain state, the Manhattan distance will be the sum of Manhattan distances of all the tiles except the blank tile. In the above slide, here, if you want to get the Manhattan distance of 2, which you can see in this row and column, you will have to move up by 1 and also right by 1, because the original actual position of 2 in the goal state is here. So, the actual row minus the current row plus the actual column minus the current column is the Manhattan distance for node 2. Heuristic score is different for each question, as we discussed before, because heuristic needs to be admissible for each type of problem. Heuristics can return sometimes the number of tiles that are not in their final position. Just as the name suggests, these heuristics can change based on the requirements. Coming to F score is the sum of the cost to reach that node and the heuristic value of that node. Basically, the summation of the depth or the cost of each move plus the current heuristic. So for any given node, the F score is defined as f of x equal to h of x plus g of x, where g of x is the cost of that node, h of x is the calculated heuristic of the node, and x is the current node. Now let's start with this initial configuration. We'll go through a visual walkthrough. There are two options to move the blank tile. Then we'll check where the f values are less, and we will move forward with the node with the least f value. In the starting configuration, the g value is 0 as it is the starting state. The heuristic is the summation of the Manhattan distance for each tile except the blank tile. Here, the nodes that are out of place are 1, 4, 5, and 8. Hence, the heuristic is 4. We add these two to get the F score, which is 5. For the next state, we have two options. We can either move the empty tile to the right or down. For both these cases, we calculate the G score, the heuristic, and the F score. Here, the G score for both the states is 1 as we made one move to reach this state. The heuristic is the Manhattan distance. The F score of the leftmost configuration is 4, which is less than the one on the right, whose F score is 6. Hence, we choose the left puzzle state to go forward with. Again, for this state, we have two possible child states. The G score increases to 2 here, as again we have made two moves. We select the state with the least F score to be in our optimal path. So, this is how G, H, and F are calculated. Coming to the algorithm, now that we know most of the terms, let's understand a generic algorithm. So the A star algorithm's main characteristic is that it keeps note of each visited node, which allows it to skip over nodes that have already been visited, saving a significant amount of time. It also has a list of all the nodes that need to be studied, from which it selects the most ideal node, saving time by avoiding nodes that aren't necessary or optimal. So we utilize two lists in general, the open list and the closed list. The open list contains all the nodes that are being formed and do not exist in the closed list, and each node studied after its neighbors are located is placed in the closed list. The neighbors are placed in the open list. The next node is chosen from the open list based on its F score, and the node with the least F score is picked up and explored. This was a generic version of the A star algorithm. We will discuss our approach in detail next. So, let's take a quick walkthrough of how the A star algorithm reaches the optimal solution and finds the path. Here we have the starting slide puzzle configuration. The starting G score is 0 as depth is 0, or the number of moves made to reach this configuration is 0. The heuristic is 3 as the nodes 4, 5, and 8 are out of their goal positions. The F score comes to 3, 0 plus 3. We can move the tile in three directions, up, down, or right. On moving the tile to the right, we can see that we get the lowest F score. We also make sure that we don't visit any state that has already been processed to avoid the loops. So we add this configuration to our path and we move forward to process its children. For this configuration, we have three options to move the empty tile again: down, right, or up. In these, we will go forward with the least F score out of the three and process its children. We found that we have the goal state with a heuristic of 0 in the next one, as we can see that only 7 was out of place in this one, and in this configuration 7 reached its place, so we have the goal state. So here we have the goal state which has been reached. Cool. Let's go through the algorithm that we have used in our code. First, we have an is solvable function to check for the number of inversions. An inversion is when two tiles are in the wrong order. So if there's a sequence like 1, 3, 4, 7, 0, 2, 5, 8, 6, then it has six inversions. So the actual order should be 1, 2, 3, 4, 5, 6, 7, 8. And as many, if either of them have any inverted um, numbers, then those are the number of inversions that we have to count. Now, if n is odd and the number of inversions is odd, then the puzzle configuration is not solvable. If n is odd but the number of inversions is even, then the puzzle is solvable. And vice versa is true if n is even, and n is basically the total number of tiles that exist in the puzzle. That is n slide puzzle, that is n equal to 9 in the case that we are looking at. So n is odd in our case because it's 9. So if the number of inversions is even, only then will that puzzle state be solvable. So this is how we check if a certain configuration is solvable or not. Otherwise, we'll just not process it. Next, we come to goal states. The goal states variable contains all the valid goal states for the slide puzzle, and we can consider that there may be more than one, but in our case, we just have one goal state, as we know. Here we also have a variable called heuristic when we create a node. So heuristic is the heuristic scale factor multiplied by the Manhattan distance. Here we have taken the heuristic scale factor as 3 because initially we discussed how we can change the heuristics based on our requirements. So we have decided to multiply the Manhattan distance by 3, and that is the heuristic that we have taken. First, we initialize the board with our root configuration for the puzzle along with the starting G score or depth, as we have taken here as 0 initially. We initialize the heuristic of the state with the scale factor 3 multiplied by the Manhattan distance. We calculate this with the get Manhattan distance function, which we have in our code. We get the goal state for the board from the goal states function. We next add the root node configuration of the tree and add it to a priority queue. We have chosen a priority queue as we will need to get the code with the minimum f value. So priority queue will be efficient for this operation as it uses a min heap. So we'll be easily able to get the node with the minimum f value. Now we loop till the queue is not empty. At every iteration, the node with the lowest f value is removed from the top of the queue, as it's very easy because a priority queue which is implementing a min heap. Now there are two options. If the current state is one of the goal states, then we clear the rest of the queue and add 1 to cur goal, the variable which was initially initialized to 0. Cur goal is the goal state that we are currently processing. So in the all the goal states that are possible, there will be several goal states with different indexes. So cur goal basically keeps track of the indexes of which goal state we are processing currently. So if cur goal is 0, it is increased at every iteration. So initially if it's increased to 1 at the first iteration, when the goal is reached, then cur goal becomes equal to goal states dot length, which is 1. So if the current goal is equal to goal states dot length, that is all the goal states have been processed, we initialize a temporary node equal to the the current node, and while temp is not null, we keep adding the board associated with the previous node of the temp node to the boards list. Once we reach null, we exit the loop. Next, so boards now contains the one of the valid paths to the goal state, because like we reverse it here and it has like one of the paths to the goal state. We add this to the final board list, which will contain all the valid paths. So if there are several goal states, there'll be more than one valid path, right? So in our case, we just have one goal state, so we'll have only one path for the final boards list. We then reverse the boards list and add it to the final boards list in 1D. Here we have done that, which is our final answer. So final boards is basically what we return from this function. We can use the path that we just returned to show the different moves that were happened, the different sliding puzzle states in our UI. Now, if current goal is not equal to the length of the goal states, that is, all the goal states have not been processed, that means we haven't reached or processed all of the goal states yet. So, another root node is initialized and added to the queue. The root node has the initial state of the puzzle, the previous is initialized to null, and the depth is 0, and the heuristic is the scale factor multiplied by the initial Manhattan distance of the current state to the next goal state. Now, if this configuration is not a goal state, then the second part will be executed. We will convert node.board to a tuple and add it to the list of visited nodes so that we don't revisit nodes and avoid loops. Children will contain the possible children graphs that can be generated from the current matrix. Here, final children. We get the children nodes by using the generate children function, which basically checks if those moves are valid or not, and if the move is valid, then it adds it as a children. Cool. So we get the children nodes and loop over these children and convert the child.board to a tuple and the previous node as the parent, that is the current parent node. We also pass the heuristic, depth, and the value of the previous node as the parent. So if it is not present in the visited list, add the child node to the priority queue. Here we check if it is there, and if it's not, then we add it to the priority queue, and then we move to the next loop iteration. So this is how it works out. Let's go through a quick walkthrough with example. We will get the first goal state. So we will first start with this configuration, and from this configuration, based on the value of n, we'll get the goal state, which is 1 2 3 4 5 6 7 8 9. Cool. Then we follow the approach that we discussed before. We create a root node with the initial current state. Then we go to the child nodes and check their depth and heuristics. Here we have the starting slide puzzle configuration. The starting G score is 0 as the depth is 0, or the number of moves made to reach this configuration is 0. The heuristic is 3, and as nodes the 4, 5, and 8 are out of their goal positions. The F score comes to be 0 plus 3 into 3 equal to 9. From here we can move the tiles in the empty tile in 3 directions: up, down, or right. On moving the tile right, we see that we get the lowest F score, that is 7. Okay. We also make sure that we don't visit any state that has already been processed to avoid loops. So we add this configuration to our path and move forward to process its children. For this configuration, again, we have 3 options to move the empty tile: down, right, or up. We go with the least F score of the 3 and process its children. We find that we have found the goal state with a heuristic of 0. So finally that we have the heuristic of 0, the place that we were checking that if we have reached, if the current um, configuration is a goal state, that condition will be fulfilled and this path will be added to the goal state, to the boards list, and will be returned finally with the final boards list. Yeah. Thank you. And in case of any questions or doubts, please reach out to us on Twitter or LinkedIn. And these are our Twitter IDs. Thank you.